Welcome back, students. We're in lesson 11. This is video A. We're moving on to probability. Totally new topic for most students, so pay attention. The main question here to start, why would we study probability? A lot of times it's a difficult subject for students to grasp, and sometimes the numerical answers may not be all that intuitive. You might get something that doesn't seem to make sense even though it is the right answer. Here's why we would study probability. When we look at statistics as a field, there's two main branches, and the one we've sort of covered already, it's descriptive statistics. How do you collect data? How do you analyze data? How do you graph data? How do you calculate summary statistics? Okay, so we've covered this in the course already. The second part is inferential statistics. If we take the whole field of statistics, we break it up into two groups. These are the two subcategories. And in one way, I've always thought of it this way, probability usually happens in the middle of a stat course, and probability is sort of the link between the two. So we'll go over here to the sideboard, draw a little picture here, just to visualize this. All right, so here's descriptive statistics. Box and write a couple notes in here. Descriptive statistics, collecting data, organizing, summarizing, graphing. It's a pretty good list there. Data. How do you collect data? Once you've collected it, organize it, summarize it, and graph it. Okay, so that's descriptive statistics. The second half of the course, the good stuff, what we're getting to is inferential. So here on the right is inferential statistics. And this, what does this word mean? It means once you've collected a sample of data, we're going to use that sample to make decisions about the whole population. Okay, so using sample data to make decisions or conclusions about a population. Remember, the population is the big group that we're interested in, and the sample is just going to be a little piece of the pie. There are two main topics that we'll cover in the second half of the course. One of them is what's called a confidence interval. If you don't know what that is, that's fine. We'll teach it to you. And the second thing is a hypothesis test. So that's the second half of the course. For roughly 2 to 3 weeks. We need to link these two. I think the link is probability. Now be careful. We can't forget about how to collect data, organize, and summarize it. But we're going to need this language of probability, so once we move to confidence intervals and hypothesis tests, the methodologies to do these topics are all probability-based. Okay, so we can't skip this. All right. Some definitions then for this video A. Go back to the main board here. All right, definitions. Let's see if I can remember what I was thinking here. Something is a repeatable action or observation that has an uncertain result. Probability experiment. Probability experiment is something that's repeatable. The result is uncertain. So really simple classical example is if you flip a coin, who knows if it's going to come up heads or tails, right? Flipping a coin is repeatable. The result, heads or tails, is uncertain. So that would be a probability experiment. The example that we'll use for this video is the MAT127 class and the attendance on any given day, how many students show up. That's repeatable, right? We have class today, we can have class next time. And uncertain results. Do we know that every student's going to show up? Will we have 1 absence, 5 absences? You sort of have to wait till the class actually happens, right? So we'll frame that as a probability experiment. All right, next one. Like I was saying, for Math 127 class, number of students that actually show up on any given day is what's called a random phenomena. I do need to get my notes here. I can never spell this word here. Number of students that actually show up. Random phenomena. F-P-H-E-N-O. Random phenomenon. Okay. We won't know how many show up until tomorrow when we actually hold class and count up the number of attendees. Okay. Now, hopefully most students show up, if not all, on any given class. All right. Clean that up. Next one down. A full class now. We have 24 students in the classroom. If you had a full class, for this example, let's pretend that we're working with a full class, full enrollment. And for simplicity, I'll assume we're dealing with that full class. Your instructor is interested in days where at least 22 students show up. She'll consider that a success. So obviously, the more students that show up, the better. At least 22 students showing up, this is called an event. It's something that we're interested in. Maybe we'll count up the number of times that at least 22 students show up. And I can have other events. Another event could be perfect attendance, for example, or exactly 7 students are absent, right? These are all events for the probability experiment. All right, moving on. Lots of definitions in probability. So every time we have class, a Math 127 class, this will be called a trial in the probability experiment. And each class, whether or not, so let's say for tomorrow's class, did we have at least 22 students show up? This would be called an outcome in our probability experiment. Okay, so every class will be a trial, and we can repeat that. And there'll be outcomes, right? Whether or not our event was met. 22 students showed up, or maybe fewer than 22 students showed up. Okay. Moving on. Let's see here. A couple of different ways to estimate probabilities. One way to estimate probabilities is by actually collecting data, which makes sense because everything in this course has been sort of data-based. All right. If I collect data to estimate probability, this would be called the empirical method. If you've ever heard the term empirical evidence, empirical means based on data, right? So empirical method to determine probability. So, I mean, I've been teaching Math 127 for 7 years now. I've probably taught 50 or 60 sections. And I have data. I could keep attendance records. And if I reference those attendance records and started counting up the times where we had at least 22 students, I could use that data to make an estimate of the chances or the probability that we have at least 22 students. Okay? Now, this makes sense to me. Hopefully it does to you. Next slide. Over time, as we have more classes, another week goes by, 2 more classes, another week, right? We collect more and more data, more results to the probability experiment accumulate. The instructor keeps a running tally of the number of classes that at least 22 students show up. If we take this as a relative frequency or a proportion or a probability or a percentage, we can use that relative frequency to estimate the probability. We take the data and then basically we tally it up, and that's our estimate. Okay, so if taken as a relative frequency, and by the way, we've worked with proportions and percentages before, so this is actually nothing new at this point. We're just sort of calling it probability. If taken as a relative frequency, we can use that to estimate the probability of 22 plus students. Okay, so down here, let's just make up an example. I'll keep the numbers easy so I can do the math in my head. For example, let's just say after 100 classes, we have 53 days with 22 plus students. So after 100 classes, down at the bottom of that page, I count them up, I keep good records. I have 53 times, 53 days with at least 22 students showing up out of 24. And if somebody came to me and asked me, well, what's the probability that at least 22 students show up? Well, I just take the relative frequency, right? Here's the notation. We put a big P. Probability 22 plus, I'll sort of shorten that because I'm going to run out of room here. Probability that I get at least 22 students showing up equals relative frequency. It's just the 53 over 100. Hopefully we can do that in our head as a decimal 0.53 or as a percentage. Easy one, right? 53%. All we did was take the data and use the data to estimate the probability. Now, I think we're going to go there, but let me just speak to that now. 100 is a good sample size, right? Lots of trials. But what if I had, say, 3 years worth of data? So instead of 100, maybe I had 500 classes that I had taught. Do you get the sense that our probability estimates might get better, right? The more data that we had, the more evidence, we would feel more comfortable in this estimate of the true probability. Okay, so that should lead us to the next page. Although who knows, I just wrote these slides and I'm not quite sure where we go with this. Let's see. One assumption required. We're going to get there. Clean this up here. Think about these probability trials. One assumption required for most every probability experiment is that the trials are independent from each other. So here on the next page, independent. And we've seen that word before when we were working with categorical variables and contingency tables. In other words, today's attendance has no impact on tomorrow's attendance. We're going to assume so just for this example. Now keep in mind, if a student misses one class, I would be willing to bet that they're more likely to miss the next class. I think things sort of accumulate, and if bad habits start skipping class might be contagious, right? But for this example, we will presume that today's attendance has no impact on tomorrow's or the next classes. So we need independence of those trials. All right, here's what I was thinking of 2 slides ago. It's called the law of large numbers. Let's write that in first. All right, the law of large numbers. This states that, and this makes sense, as we complete more trials, in other words, as we collect more data, our relative frequency estimate of the true probability should tend to get closer to the true value. So if I make an estimate for at least 22 students showing up, probability after only 10 classes, my estimate may not be very accurate. If I get to 100 times, more accurate, and if I just kept collecting data, 1,000 classes, 2,000 classes, law of large numbers simply states that my estimates will get better. Okay? And it says it here. And down at the bottom, for our example, as we hold more MAT127 classes, the estimates of that probability will become more accurate and more reliable. All right. A couple more, I believe. Yep. There are actually 3 different ways to estimate probabilities. The first we learned was empirical. That's by data. A second way to estimate the true probability of an event is to use what's called subjective probability. You've heard this word before, subjective. This method's not based on data. It's based on your personal opinion. It's based on subjective belief of the likelihood of an uncertain outcome. If we had no internet connection, no TV, and I said, what do you think the chances are it rains today? And you poked your head out the window and it was kind of cloudy and kind of windy like it is today, and You might say 80% because it just sort of feels like 80%, right? That's subjective probability. Completely different than basing it off of data. Here's a Cecil College example. Suppose I'm just walking down the halls and the dean at Cecil College asks me, what's the probability that a Math 127 class has at least 22 students in attendance? And off the cuff I just reply, well, it's about 80%. It's my best guess. I can think about all the classes that I've taught. I can sort of just do a rundown in my head. What's the chances there's only a couple absences? And, you know, about 80% is probably pretty close to the right answer. This is based on personal experience, and it would still be my best guess without any data, but it's subjective, right? You can see the difference between this way and actually tallying things up, keeping records, okay? No data was used, then it's subjective. One last way, and then we'll wrap up this video. There's a third way to estimate probabilities, and that's what's called the classical method. So a third way to estimate true probabilities is called the classical method. Using this method, we assume every outcome is equally likely. Using the classical method, you assume all outcomes of the simple events are equally likely to occur. Okay, now, let's try to think of an example for that one. If I think of our attendance example, Math 127, classical method would fail because it assumes every outcome is equally likely. In other words, it's just as likely for me to have 22 students in attendance as it would be to have 3 students attend, or no students, or all the students. Everyone would be equally likely. And as an instructor, certainly this isn't the case. I hope it's not the case. I know it's not the case. But to do classical, then I would have to assume that every outcome is equally likely. There's a 1 out of 25 chance that I have perfect attendance. A 1 out of 25 chance that I have 1 absence, 2 absences, all the way down the line. Okay? That's not going to work for this example. Where does classical work? Dice, cards, lotteries, flipping coins, classical method. Let's roll a fair die, for example, to wrap up this video. So, probability. We're going to roll a fair die, 6-sided cube. So, probability that I roll a 1 is actually equal to the probability that I roll a 2, which is equal to blah, 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 blah. Probability that I roll a 6. They're all equally likely. And if there's 6 sides on the die, then the answer is 1 out of 6. Presuming the die is fair, it's just as likely to roll a 1, 2, 3, 4, 5, or 6. So classical method. Okay, equally likely outcomes. And with that, we'll wrap this one up. Kim Shepard will be on in just a bit to tell you about some different ways to calculate probabilities. See you in class. Thanks for watching.